The latest ViDiLabs test chart comes in A3+ format, as the previous ones, mounted on hard but light mounting board for easy positioning in your workshop or labs, but also for easy shipment around the world. We even add one more strong board for further protection during shipping. If your project requires, you may also order the chart in double the dimensions of A1 size, although shipping and handling might be a bit more expensive, but we can certainly produce larger formats if you require. Before you start testing, you need to position the camera perfectly, perpendicularly to the center of the test chart. Looking at the center of the test chart, covering 100% of the 16:9 aspect ratio section. If you are testing high definition or ultra high definition cameras, the 4K, but it is also possible to test 3:2 or 4:3 aspect ratio camera signals of up to 12 megapixels. Illuminate the chart equally from both sides using good quality LED illuminators and measure the lux level. Ideally, for resolution measurement, you would require 1000 luxes reflected light as per the standards. Record a short video and then export an image from it. This could look something similar to these examples shown here. We can then run the software to analyze these images and obtain the results as plots and graphs, which we can email to you. Okay, so let's launch the software, which is written in MATLAB. MATLAB is a program that does a lot of fancy mathematical calculations. So this is the ViDiLabs MATLAB code. It goes a few hundred lines. The way how we test is basically the image that we exported from the camera that we want to analyze. We just run it through the software. And in this case, I will take, let's say, this image, which looks like that. This is just a preview on the computer. So we'll run it. The software says it's busy in the bottom left-hand corner, so it only takes a couple of seconds to analyze this. And here is the result. So this image now is analyzed image of the test chart export. Now we've got a few windows here because the software does 5 different graphs. But I'll explain this one, which is the first and most important one. So here's an image exported from a camera that we wanted to analyze, that took picture, obviously, of a test chart in front of it, properly aligned. As you can see, it doesn't have to be perfect alignment. It may be slightly off, but obviously the better you align the camera relative to the test chart arrows, the more accurate results would be. But the idea with the sine wave Siemens star is that even if you've got an error, the actual calculation is more accurate with the Siemens sine wave star rather than the curvy wedges we have also, which was like in the past. But this is only for visual determination of the resolution. With the software, we actually can get very accurate software measurements. Now, just before I explain the actual measured parameters here, I just want you to be aware of this black to white to black bar. This is used for measuring the transfer curve of a camera, and it's supposed to be linear from black to white in the middle, and then again from the white to the right, linear to the black. Then we have 11 steps of gray going from black to white. Remember and pay attention to the middle patch here, which is at 50% gray level. We measure actually noise at this point, and you will see how that is done. Then we have at the top, like in the previous test chart, we've got the known television color bars, which are pure red, green, and blue images. And the actual software, as you can see here, it's actually measured their deviation from the actual pureness. The actual test chart, when printed, is printing this for the yellow to be with 255 units of red, 255 of green, and 0 of blue. But in this instance, as you can see here, the software has measured 251 for red instead of 255, 249 for green instead of 255, and 68 units of blue instead of 0, which calculator comes up with the deviation of the color to be about 3%. This is basically the error of the color reproduction in this particular color bar. We also measure similarly to that with the Macbeth chart. Macbeth chart is a known standard in photography, so our test chart has got very precise and accurate color with defined values, which are not pure colors like the television bars, but these are used mostly for photography, for reproducing of skin tones, and it's kind of in between red, green, and blue. So, for example, if we get this particular patch, the Macbeth test chart has defined this chart to be with 214 units of red, 126 of green, and 44 of blue. The actual software we designed actually measures slight deviation from it. So the camera that looked at this particular Macbeth color chart says, well, I'm measuring here 226 instead of 214, green 125 units instead of 126, and blue 73 units instead of 44, which is variation of about 4% of delta E. So that way you can very convincingly check the color balance of your camera. I know in CCTV we are not maybe that picky with having good color reproductions, but certainly in certain projects like banks where we're handling money, or maybe in the textile industry where you need to have very good understanding of what is the color that the camera is seeing, you may use such a chart to make sure that the reproduction is as close to the real life as possible. So this is the first chart. Now we are not doing any analysis of the software, of the money and the coins and the play cards, because this is really for visual analysis, which is later on you will see explained in the manuals. But certainly we have a reproduction of money, which are in this instance, when you order the test chart at a normal shipping size of A3, these are exactly half of the real value. So basically you come close to viewing the test chart exactly to the half relative to the beginning, then you will see this money and cards in the actual real size relative to the sensor and positioning of the camera. But in any case, this is the very first image, the very first calculation window. Then we have the actual resolution is actually more accurately shown with this graph, which is called modulation transfer function, MTF in percents, versus the spatial frequency response, which is measured according to the new standards as line pairs per picture height. So the green squiggly line here is actually the center Siemens star, and it's actually crossing the 10% value at a point which is 393 line pairs per picture height. That is the limiting resolution of this particular camera exported image based on the IEC standards. We measure the modulation transfer function down to 10%, and this is the closest one, and that tells me that the center resolution of this test chart is about 393 line pairs, which is equal to about 786 lines, but with the new standards we are measuring line pairs per picture height. Mind you, the maximum resolution you can have with a HD signal is 540, because 540 is actual 1080 vertical lines, so in line pairs that will be 540. So as you can see, we are measuring all corners in terms of Siemens star resolution, top left, bottom left, and so forth, and you can see the differences. Sometimes based on these differences you can judge the perpendicularity of the sensor relative to the optical axis. In fact, we have found in our many experiments and tests in the past. Some camera manufacturers don't have perfect alignment of the sensor relative to the optical axis, and if your alignment is proper in terms of setup, when you measure the test chart, you may notice that particular camera models may have either the left-hand side or the right-hand side sensors completely out of focus relative to the center one, pardon me, which may indicate that you've got alignment of the sensor as an issue. Next is the 11-step grayscale. As you can see here, it's quite easy to explain and understand this. The black steps are actually the reference 11 steps, where you've got from 0, the black level, to 255 level, which is for the white. The red dotted one is what the camera has produced. So as you can see, the camera has produced a little bit out of what you expect, which means you can't really show the black as what the black is, and you're squashing the top white level to 225 binary levels, which is about 88%. So in any case, this gives you some idea of the gamma of the camera, and this is a bit more accurate. This is a bit more accurate gamma, but we call it transfer curve. So remember the strip of black to white to black. This is represented with a green triangle, which means this is from the black to the peak of 255 white, back to the black again. The actual camera has seen this type of shape curve, which is, as you can see, not only squashed in the white and uplifted in the black area, but actually is slightly deviating from the linear one, which is not a big problem, I guess. When you see normal picture, that doesn't really matter that much. But if you want perfection, in a way, you can determine which camera has a better transfer function relative to the others. And finally, we also measure the noise level, which in fact is signal to noise for that illumination. We remember the middle patch we mentioned, patch number 6. We calculate the variation of the luminance of the grainness there, and we found out, the software found out, that there is about 0.7% variation, which is in decibels equivalent to 43.1 decibels. When you get a calculation of similar noise in cameras with higher noise, obviously this number will be much lower because the variation will be higher, so that means signal to noise will be higher, but obviously the signal relative to the noise will be much lower if it is low light. I'll show you that with one picture tested at very low light when we were doing the minimum illumination measurements. The software calculates this one now, and you will see this is a picture of a camera taken in a low light when it's generating only about 30% of the video signal, and this is shown here. That means, according to the latest standards, in order for us to find what is the minimum illumination of a camera, we need to bring the signal down to produce only about 30% of the signal of the level, and that 30% looks like this. Now, as you can appreciate, the actual noise here is quite sort of visible, but we also measure that, and at that low light level, the actual noise is about 4%. So the decibel ratio is 27.96 signal versus noise. So obviously you want this higher and you need the variation lower. And that's an example of how we do camera measurements with the ViDiLabs software. Please send us your images and we can find the actual quality of your camera or the setting of a particular camera and send you the results back for free. Thank you for watching.